Hello, my name is Hamid Rastgoo and I'm going to be representing Universiti Putra Malaysia in this year's Materials Lecture Competition 2021. So my topic is going to be about laser joining of dissimilar materials, and my presentation is going to focus mainly on three keywords from the topic itself: laser, joining, and dissimilar materials. Ironically in that order but reversed. So first of all, we're going to be talking about dissimilar materials, what they are and how we can identify them. Then we're going to talk about the different joining methods that have been established throughout time and what are the more recent ones that are used today. And finally, we're going to be talking about lasers and their role in the grand scheme of things. So without further ado, let's begin. So in order to talk about dissimilar materials, we're going to answer two main questions to help us understand this topic even better. So first of all, we're going to answer what are dissimilar materials and how we can of course identify them. Then we're going to talk about what is the purpose of joining them, because as we go along, we're going to understand that it's quite difficult to actually merge and bond dissimilar materials. So we're going to establish the main motivation behind it. But first off, we're going to talk about dissimilar materials. So generally speaking, materials with different core properties are often categorized as dissimilar materials. Some of the famous examples are metals, polymers, and ceramics. However, before we move forward, it is really good to know that it is very much common and possible for one or two or even more materials within the same group to be categorized as dissimilar materials as well. For instance, we have carbon, steel, and aluminum. Obviously, they're both metal, but because of the differences in their composition, they're often at times very difficult to bond together, which is why we put them under dissimilar materials as well. A little bit of a side note as we go along. So now that we've established what are dissimilar materials, which in a basic description they are materials with different core properties, we're going to tell and ask this question, what is the purpose of joining them? So the main goal here is to have a set of properties into one single component. Now what does that mean? Well, nowadays emerging trends such as lightweighting, performance, and functionality demand the use of hybrid and multi-material structures such as dissimilar materials. So to give one example, when we have plastics on one side or polymers and we have metals on the other side, these two different materials have different characteristics. For instance, polymers are very light, but at the same time they don't have a really great strength to body ratio. And on the other hand, we have metals where they're very strong, but unfortunately they're also very heavy. So what dissimilar materials actually does is that now we can ponder the question, can we get the lightness from polymers and the strength of metals and combine these two main advantages into one single entity? Well, the answer to that question is yes, we can. But it's a little bit more difficult than that, which is why we transpose into joining of dissimilar materials. Now, from this hierarchy, we can actually see that from the start, it separates into two different groups. One, we have conventional methods, and the other, we have non-conventional or modern methods. So the biggest difference between these two are that conventional methods are often at times used for short-term solutions, meaning that whether we use mechanical fasteners or adhesives to bond dissimilar materials, they usually at some point get weakened and they become almost useless, which is why in order to prolong their life, we either need to have considerable amount of maintenance or we need to redo the process. To fix this issue comes a much more cohesive method, such as non-conventional methods or modern methods, as some people put them. So underneath modern methods, we see thermal fusion joining and hybrid joining. We're going to focus on thermal joining because hybrid joining has entered the game very early on, and it's a little bit of an unstable position, though it has a great future. But for now, under thermal fusion welding, you can see it has a lot of branches, starting from friction welding to high energy beam welding. And underneath high energy beam welding, we can see laser joining. So looking at this hierarchy, we can see that laser joining has actually come a very long way, and it has a lot of weight on its shoulders. From the process at the beginning where we had conventional methods to today that we're using most of the advanced technology that's within our grasp to use lasers to join this method. So the evolution of joining of dissimilar materials has actually come a very long way. It has evolved through time and it has adapted to the latest technology of its time. To what are we using? To what we're using lasers as of now. So finally, with that said, we can jump into the main topic that we've been trying to get to, and that is laser joining of dissimilar materials. Now, in order to understand this better, we're actually going to answer three main segments here. We're going to talk about a brief history of lasers. Then we're going to talk about the fundamentals of laser joining, basically to have a great understanding of them. And finally, we're going to give a very brief example of a laser joining between two dissimilar materials. But first off, we're going to talk about a very brief history of lasers. So to start off, I cannot stress this enough. The man himself, Professor Albert Einstein, was the first person to suggest the fundamentals of lasers. However, since he was ahead of his time, it took almost more than 40 years until finally Dr. Theodore H. Mayman was able to build the first ever laser prototype. But once that prototype was built, we actually kind of segued into the third industrial revolution, where technology was enhancing much more than anyone expected, which is why many people saw the idea of lasers and they wanted to experiment with it on various different environmental categories. One of them was similar welding. So in this case, in the beginning of the third industrial revolution, many began doing experiments on similar materials such as metal and metal and polymer and polymer. And those experiments were actually quite successful. Successful enough that it came to no surprise, only a few years after that, people saw great potential in it to start experimenting for lasers on dissimilar materials such as metal and polymer, or even ceramic and metals. And mostly going forward, we actually saw that towards the end of the 20th century, many of these industries began to look at laser welding from a very different perspective. They saw it had a lot of advantages, so they started investing a lot of money and time into a lot of researches, which is why at the beginning of the 21st century, we saw a huge amount of breakthrough in investigating laser joining from a molecular and atomic level, which was tremendous. This gave a potential gateway to understanding lasers on a whole different level. We can see that on this point until here, the industrial aspect definitely was satisfied with laser joining. It had a lot of industrial attributes, and it was performed, and it had quite a good performance when it came to mass production. But definitely some people saw great potential within this category that they wanted to extend this research on, which is why a little bit further down the line in 2014, we were actually able to identify the main parameters of laser joining. And this is a breakthrough in its own right as well, because what this did is actually solidified laser joining in the whole grand scheme of laser materials and of course materials science. From this point on, anyone who wanted to do any kind of laser experiment, they just had to refer back to these parameters, and the results would be enhancified by double. Well, basically, they would be enhancified. But of course, nowadays, once we entered the fourth industrial revolution and began seeing a lot of technology in the realm of software or finite element method, laser joining also joined them. Nowadays, people are doing experiments on softwares and they're doing simulation-based analysis. So technology has definitely been adapted with laser joining. It's definitely not something that has been left back behind, and people are continuously moving forward with this idea and researching it to this day. But moving forward, we have the fundamentals of laser joining. Now, ironically enough, laser is actually an acronym which stands for light amplification stimulated emission of radiation. So what this basically means is that basically what laser does is that lasers, they turn light into a focused high energy beam. So we have a huge power source, which is light, and all the entire concept of lasers, what it does is that now we focus that amount of light into one specific heat affected zone, which is full of energy and full of heat. And what that does is that when we point that small spot into any material, we can see that it changes the physical and chemical contributions of that material, which is basically the main concept of lasers. to understand this even better, we have three main criteria and characteristics which revolves around laser joining of dissimilar materials. So any kind of high energy beam welding that consists of these three main parts, such as mass production, a non-contactless process, and so on, these three main categories will usually adapt into having a laser joining process. A good information to have as we describe one particular example of laser joining. So in this segment, we're actually going to go a little bit into detail. We're going to specifically explain one particular example of laser joining. So in this case, we have polymer and metal, where the polymer resides on top of the metal product. What happens now is that once we turn on the laser starts passing through the polymer, which resides on top of the metal, and it starts to irritate the polymer. And in the second stage, we see bubbles forming around it. Now this happens because we understand the relationship between these materials. So once these bubbles start to come up, we see that the laser, the amount of heat that it has generated, has actually passed the boiling temperature of the polymer, but still hasn't quite reached the melting temperature of the metal beneath it. Going forward, we see that these number of bubbles actually expand, while the polymer, which is on top of the metal, actually starts to melt. And while it melts, it turns into a liquid form which surrounds the metal, and thus that molten polymer is now completely surrounding the metal surface. And once it does that, we actually no longer need the laser, we can turn it off. And once it does that, because the temperature surrounding the room is much more cooler than the temperature surrounding the materials, the liquid form starts to solidify. And once it does that, it also hardens the bonding between the two materials and almost forms a permanent bond between the polymer and metal. So this is something that is known as a laser transmission joining. Through a very simple process of pointing a laser at two materials, we've actually combined two main characteristics of polymers and metals into one single entity, where we have a product which is not so heavy, but at the same time it's quite strong, which is ingenious. But with that said, we can now have a conclusion. So in the end, first, to recap everything, first we talked about dissimilar materials, what they are and how we can identify them. Then we talked about the purpose of joining them, because it was too difficult to join them, and so there had to be a proper motivation behind it. And finally, we talked about the different joining methods that have existed through time and how it's evolved to laser joining that we're using to this day. And all of this leading up to laser joining of dissimilar materials, where on the surface, yes, it is a topic where we're using high energy beams to bond two very different materials, but on a much more deeper and intellectual level, it's actually about understanding the relationship between these different materials. Because what laser joining does is that once we point that laser into these different materials, we can start seeing their physical and chemical properties change. And once they do that, we start seeing some of the more deeper layers of materials being unraveled. And thus we start finding some of the hidden secrets in materials which we've never seen before. And understanding those secrets, and then understanding what happens on a molecular and atomic level when we heat up two materials using lasers, is what expands our knowledge on materials science as a whole. And that's why a much more deeper meaning to this topic is expanding our knowledge on material science. But of course, it has many industrial attributes that many industries have used in the past, such as automotive and aerospace engineering, and it will continue to do so moving forward. In fact, it's comprising enough as technology grows, this process is actually being enhanced with it. But it is that deeper meaning that has affected many engineers and scientists, such as myself, to research this concept in a much more deeper and in a much more detailed manner. And with that said, I would like to thank you for listening. Thank you very much.